Hello, good morning, everyone. Right. So we will continue with our sessions for the finite element methods. Today, we will start with another topic on the beam elements. So as we can see on the previous weeks, okay, we have derived from the springs, okay, to a prismatic bar, okay, where we have derived the displacement functions. Then from there onwards we have the shape functions and other things, okay, that are related to the prismatic bar. And from that we can see that using those equations, using direct stiffness methods, okay, we can easily solve for engineering problem involving the structural problem, right? So you can see that there is a truss problem, okay, you have three prismatic bar problem that you have shown and discussed previously, right? So today we move on to another part, right, to increase our luck, right, to cater for what we call it as a beam element, right? So here is the recap on what we have gone through previously on the prismatic bar, right? As I've shown you in the LISA FEA itself, there is a line tool, okay, which is, we call it as a beam or truss elements, right? So you can see that again they call it as a beam, right? Not exactly a bar, right? Even though it is a, you can treat them as a yeah, a bar as well, okay? So what is the difference between this beam as well as the prismatic bar itself? We can just look back at the prismatic bar first, okay? So along the selections of the prismatic bar itself, we define that the forces, okay, is acting along the directions of the axis, okay? So we have the tensions across, or yeah, this acting along the axial directions of the bar. So whenever there is what we call vertical forces, okay, vertical forces, okay, to sustain certain load, or maybe, and due to that there is a moment acting on the bar itself, this so-called prismatic bar may not be able to handle, okay, it will just collapse by itself, okay, because they don't have the reaction force in the vertical as well as the moment in the vertical direction. So you can see that the displacement function is very straightforward. It's just a two unknown parameter displacement functions, okay, that you can use, okay, to predict the extensions of the bar, okay, due to the tensions, okay, acting along the axial directions, okay, so it increase linearly, right? So the bar finite element equations have been derived, okay, using the direct methods, okay, but for a general knowledge for you, you can actually further derive it, okay, using different methods, okay. For example, you can use the potential energy methods as well as the variable principles like the famous Gallatin's residues methods, right? So those are some of the methods that has been implemented, okay, in the finite element software, okay. So now come to the beam element, okay. So since as we say, the prismatic bar itself has a problem that it cannot sustain any vertical directions or transverse type of force, okay. Therefore this beam elements is derived, okay, to handle that, okay. For sure the beam, as we learn from the strength of materials, it is related to structural member, okay, a straight structural member. We usually say it's a long and slender type, and it is used to subject to a transverse load, okay. If it is subjected to a transverse load, we usually call that as a beam itself, okay. Therefore the beam, the purpose itself is to sustain the the load in the vertical directions, right? Whereas the twisting as well as the axial effect, okay, or displacement in the longitudinal directions or the axial directions may not be that significant. Okay, so most of the loads or forces are acting in the vertical direction. So therefore, when we select the proper final elements for this kind of problem, then the best one would be the beam element instead of the prismatic bar, right? So the bending deformations, okay, since we apply a vertical force over here or maybe at the middle, so this beam, okay, will be subjected to a bend, okay, we call it bending displacement. So if this is the case, then as you would expect, it will bend in this way, right? Okay, so this bending itself is subjected to a transverse displacement. Okay, you have a displacement in the vertical direction as well as a rotations. Okay, so you can see that the axis itself is now rotated, okay, slowly rotated. Okay, so therefore for every single node itself, okay, we should consider 2 degrees of freedom. Okay, there are transverse displacement as well as a rotation occurs, okay, on the beam element. Okay, so as this picture shows a prismatic bar element, okay, that's why the T is still there, right? So when we intend to derive it, okay, or formulate it for a beam element, therefore we would consider the forces and the bending moment at the node. Okay, so we have node 1 and node 2, right? So consider the length of the beam element with the length of L. There is a x coordinate, y coordinate, right? Then since we are looking at the transverse displacement, therefore we should define this y axis as well. Okay, so this y axis now will tells us what is the nodal displacement, okay, the displacement at the node, okay, given by v1, okay, v1 and v2, right? And this v1 is due to the force, okay, f1y, f2y, okay, and also there is a rotations, okay, so rotations at the node itself, okay, so the rotations at node 1 and node 2, okay, given by psi 1 and psi 2, okay, due to the moment at node 1 as well as node 2. Okay, so there are 2 type of force, load itself. Okay, there is moment and the force acting at node 1. Similarly, there are force and moment acting at node 2 that cause those displacement as well as rotations, right? So again, the beam theory sign conventions are applied, okay, for on the left hand side. Okay, so we will put the shear, okay, the V, okay, is along in the positive directions, whereas on the other side is the negative directions. Then the moment would be defined such that it causes the beam to bend in these directions. Okay, so we just use the conventional sign conventions for a beam theory, okay, to define for our beam elements, right? Okay, so just a brief ideas on the beam theory itself. Okay, so the beam theory here is mainly defined by what we call Euler-Bernoulli beam theory. Okay, a very famous Euler beam theory itself. Okay, that considers only the beam deformation in this case. Okay, so we only consider the bending deformations. All right. So the main assumptions, okay, that have been taken when we derive this is that the cross-sectional area, okay, when we cut through it, okay, when we review the cross-sectional area, okay, so this is the so-called cross-sectional area, right? So when you cut through it, you may have, let's say, an I-beam, right? So you may have a cross-sectional area. So this cross-sectional area, okay, when we cut through it, or we say a plane through the vertical line, okay, should remain the same, okay, even before and after the bending. Okay, so when you cut through it, okay, so point 1, point 2, or in point 3, so you cut through it, right, cut through it, okay, through the so-called perpendicular to the bend x-axis, okay, so 90° to it, right, 90° to it, right. So this cross-sectional area should remain unchanged, okay. So that would be the best, the first kind of assumptions in these derivations, right. So from that onwards, okay, so let's take this, there are a force and moment acting on the differential element. So we just cut through one section of it, okay, we take one so small sections of it, okay, to we call it as differential beam elements, right. And then from there, as we can assume, we take a distributed load acting on it, right. So there is a distributed load acting on the small sections of it, or we call it as a differential elements of it, right. So from there, the differential equations can be derived as such, okay. So the first thing is we just take summations of forces acting on this differential beam elements free body diagram, right, should be equals to 0. Similarly, the summations of moment acting at any chosen point itself should be equals to 0 as well, okay. So once we have taken that into considerations, therefore from this free body diagram we can know that the V, okay, minus the changes, okay, then minus the distributed load, okay, should be equals to 0, okay. So from there you can get this and this, right. So same thing for the moment, take moment at node number 2, therefore the summations of moment, okay, should be given by the V multiplied by the length, okay, dV, okay, then dm itself, okay, the changes due to the moment, okay, the dm, right, plus the so-called due to the distributed load should be given as such, alright. So and the summations of them should be equals to 0, right. So from there we can simplify such that the V equals to dm over dx, okay. Then we consider the curvature of the beam as well. It can be defined as the 1 over rho, which is the m over ei, okay. So now the derivations from the Euler-Bernoulli's theorem itself, they relate it with the Young modulus and the moment of inertia, right. So from there onwards, okay, you can see that the curvature itself is given by the dv square over dx square, right. So this is the curvature of the slope, okay, given by this the slope dv over dx, okay. So therefore from here, right, we can relate, okay, this curvature equals to MEI, okay, MEI, right. So once we have relate this with the MEI, therefore we can formulate the importance equations over here, right. So the moment at any particular point across the x, okay, will be equals to EI dv square over dx square, okay. So you have this second order derivative, okay, of the V itself, okay. So further on you can further derive, and when the constant of the EI is applied, therefore our equation should be equals to 0, okay, for EI dv power to 4, okay, over dx power 4, right. So this is the idea behind the beam theory itself, okay. So now we start to relate back to what we intend to, okay. Our purpose is to use the beam element as an element in the finite element methods. Okay, so first thing, when we select the elements, we have now applied a different type of element with different degree of freedom. So here you can see that there are 4 degree of freedom, 2 at one side, okay, or 2 at each node itself. Okay, so 2 and 2. Therefore, when we select the displacement functions, we would apply 4 unknown parameters for our displacement functions, right? So you have a1 until a4. Okay, so given by as such, right? So if we further re-express them with respect to the degree of freedom of v1, v2, psi1 and psi2, eventually we will get this relationship. All right, so once we get that relationship, what we need to do is we have to solve the equations 4.1.3 simultaneously, and from there we can re-express, okay, the whole displacement functions, okay, which relate to a1, a2, a3 and a4, okay, into this form. Okay, so this is the complete form of the displacement functions for the beam elements, right? So again, you can re-express them in terms of matrix. Okay, you have the displacements, okay, the v, okay, functions equals to the n, okay, matrix multiplied by the displacement. Okay, so this is the displacement of the displacement parameter at the nodes itself. So you have the displacements in the vertical as well as the so-called rotations at the node 1. Okay, same thing for the node number 2. Okay, so this is the d itself, okay, where this n is given by n1, n2, n3 and 4. So what this n itself, this refer to the shape functions, right? So it tells us how it looks like, okay, on the contributions of the displacement by every single component. Okay, so it is given as such. All right, so you just rearrange them, you should get this shape functions in this way, right? So if we again take into the consideration such that we know that the summations of shape functions, okay, at certain node, okay, should at any given node should be equals to 0, right? So if let's say we take at node number 1, okay, at node number 1, and we say that the what we call the length, okay, node number 1 is at the beginning, the length should be equals to 0, right? So therefore we would review that the n equals to 1, right? Whereas the n2 equals to 0. Okay, so eventually the summations of n1 and n2, okay, as well as the others should be equals to 1 as well, right? So that would be tells the to verify the summations of shape functions equals to 1. Okay, then next would be the starting with the definitions of stress, strain as well as strain displacement relationships. Okay, what we have derived so far is only related to the displacements across the element itself, right? So how we can define the strain as well as the stress itself, we apply our relationships. Okay, so we have this for the beginning, we know that the strain is equals to the displacement divided by the original distance, right? Then from here, for the transverse type, okay, for the transverse type, therefore we can define as u equals to minus y dv over dx, okay, for the transverse. Okay, so therefore from this, when we substitute it into these equations, Okay, therefore we get this relationship between the strain as well as the displacement, okay, the transverse displacement, the V itself, okay, across the length of the beam. Okay, then from the beam theory, okay, that we have seen previously, remember I say this is the important relationship that we will use, right? So we have derived this from the previous beam theory, that you use this relationship to define the moment for every single relate it the moment with the strain, okay, or maybe the displacement itself, okay, by multiplying it with the E and I, right? So same thing for the shear side, okay, so the shear is basically the dm over dx, okay, so you further differentiate this whole equation respect to x, therefore you will have d cube v over dx cube, right? So further differentiate it, right? So this is what we get, right? So in the finite element analysis software itself, okay, you have tried to define the parameters for the material, right? So usually you just define the Young modulus, okay, but in this beam element itself, okay, whenever you select the beam element, they will not ask you for the moment of inertia, the I, okay. So how would the software get the I? Okay, so basically when we draw it in the computer, okay, so when we draw it in the computer itself, okay, you may have the shape itself, right? You may have a shape itself, okay. Therefore from this shape, okay, they can roughly estimate the moment of inertia for the cross-sectional, okay, area for the computationals of the purpose of the computationals of the stress and strain in the software, okay. But then if you only define it as a two-dimensional elements, okay, not three-dimensional, then in this case you have to define the I, okay. They will ask you for the I itself, okay. So further on the element stiffness matrix, okay, so from our previous nodal and beam theory sign conventions, we can further just substitute in, okay, all the ingredients, okay, that we have formed previously, okay. So put them in, all right, so you should get in this formulations, okay, for force acting vertically at node 1, okay, should be equals to this, okay, and that should be equals to this, okay. So just put them in, right? So eventually if we group them into a matrix form, then you will have this we call the stiffness matrix or equations to represent one single what is this beam element, okay, one single beam element, okay. So only one single beam element is given by this relationship, okay, that define the relations between the force with the nodal displacement, okay. So again, this we call it as a stiffness matrix, okay, where the axial effect is neglected, okay, because you can see that we only consider the vertical as well as the bending. We don't consider the tension as well as how the shape change, okay, across the cross-sectional area, right? So from this stiffness matrix itself, again, you can see that it's 12 6 12 6, okay. Then you can realize that they are a symmetrical matrix, okay. So 6 and 6 similar, okay, similar, right, same, right, same, okay. So they are a symmetrical stiffness matrix itself. Okay, if you would want to include the effect of transverse shear, okay, then you have to apply the Timoshenko's beams theory as well, okay, and that would be in this form. Okay, this is just for additional knowledge only. Okay, so now once we have the so-called the stiffness matrix, the relationship between the force and the displacement, now we can assemble our elements equations, okay, to form the global equations. Okay, so the steps now is very obvious. You can just apply the well-known to you the direct stiffness matrix method, okay, to form this. Okay, so let's consider these examples, okay, where you have two elements, right? So since in this problem itself it is straight, and then in the middle there is a force, okay, and there is a bending moment, okay, acting at node number 2. Okay, therefore the best way is we break them into two elements, okay, element number 1, okay, and element number 2, okay, with 3 nodes. Okay, so node number 1, node number 2, okay, node number 3, okay, and we label the element number 1, element number 2. Okay, so now from here onwards, okay, this part is represented by what we call reaction force, right, to represent the wall itself. So therefore you may have a bending moment as well as maybe a reaction force, okay, acting vertically. Okay, then you have on the other side you will have a reaction force. Okay, this is a pin type support, so you can rotate, so no bending moment reactions. Okay, for this there is reactions and the load. Okay, so this is how you can form your free body diagram. Okay, so from that free body diagram now what you need to do is just fill in the stiffness matrix, right? Okay, for element number 1 equation is as such. Okay, element number 2 equation is as such. Since the length is the same, so everything is the same, right? So what you need to do is just assemble them together using direct stiffness methods. Okay, the important thing is the labeling of the node, right? So for the element number 1 is connecting node 1, 2, then element number 2 is connecting node 2 and 3. Okay, 1, 2, 2 and 3. Okay, so make sure you assemble it to the right positions. Okay, therefore you can form this global stiffness matrix, okay, as well as the relation between the load as well as the displacement. Okay, so again, once we have that, what you need to consider is to add in the boundary conditions. Okay, at this point, as we say, no rotations allowed, therefore rotation equals to 0. At the same time, at this point there is no vertical displacement allowed, so v equals to 0. At node number 3 we don't allow any displacement in the vertical directions, so we put this equals to 0. So 1, 1, 3 is 0, 0, 0. So what we need to do is we substitute into here. This is 0, this is 0, okay, and this is 0, right? So leaving only this as unknown, right? So this is related to line number 3, 4 and 6. Okay, 3, 4 and 6. Okay, 3, 4 and 6. So what you need to do is you just group, or we can partition this, okay, to form your relationship. Okay, so from there you can substitute whatever known and unknown, okay, into your equations, okay, and solve them simultaneously. Alright, so you should get what you did. Okay, so any questions so far at this moment? Okay, so while waiting for your questions, I will continue with a few examples. In these examples, I will not show you the solutions, but I will only show you what are the how you can form the free body diagram to start with your uh, beam stiffness matrix and then assemble them together, right? It's just an idea of it, right? So first thing you can see from this free body diagram itself, they are a bar, okay? In the middle there is one roller, okay, supporting at the middle, okay? So what you can do is, since they are a support at the middle, therefore you can replace this as reactions, right? So as we know, for any element itself, okay, we do not put any force or load at the middle of the element, okay? If you have an element, okay, we don't put a force at the middle, okay? We cannot solve it because our derivations is only for the node, okay? Our derivation is only for the node, okay? Therefore, what you can do is, if there is a force acting, we should break them into different element, right? So you may have this as a node number 1, node number 2, node number 3, right? Element number 1, element number 2, okay? Break them into this way, right? Then put in whatever you seen, okay? You can see there are direct load acting, okay, P. Then the rest is, we have to remove all the supports, right, and replace them with the suitable reaction force. So since this is a roller, therefore we expect it's only constrain the movement in the vertical direction. So here you can say the U2 must be equals to 0, right? Okay, but then there is a reaction force, right, R2, okay, or maybe Fy2, okay? Then at the node number 3, again this wall will hold the beam from it to fall down, okay? Therefore at this particular node you will have a bending moment, okay, M3, okay, as well as Fy3, okay, to hold it, okay? Then you can see that at this particular point the displacement should be equal to 0, okay, and there is no rotations, okay? So these are the boundary conditions that you can apply, and these are the forces, okay, that you may know and you can put it in, okay, into your equations, okay? So you just form as what you have learned previously, okay? Two elements form the stiffness matrix, assemble them together, fill in whatever boundary condition that you get, and you can solve them simultaneously, right? So next is another examples, okay, where you have a long bar, okay, at the middle is supported, okay, and at the other middles there are forces, okay, acting at the middle, okay? So again what you need to do is break them into 1, 2, 3, 4 and 5 nodes, okay? So you can easily break them into 5 nodes, okay, and then label them into element number 1, element number 2, 3 and element number 4, right? Replace, okay, this load remain there, okay, replace this wall with a reaction force, okay, as well as a reaction force and moment, okay? Same thing for this wall, okay, you may have a reaction moment as well as a reaction force, okay? At this node number 3 you can replace this roller with a reaction force, okay, Fy3, okay? So that's complete the whole free body diagram, okay? You can remove all the wall and the roller, okay? So this is how you would expect, okay, Same thing for the fourth one, okay, very similar, okay, node number one, node number two, element number one, element number two, and you can represent this as the beam element. You select a beam element for this, okay, another beam element for this, right? But then the only difference is that there is a spring acting over here, right? So what you need to do, or what you can do here, is that you add an additional spring element. Okay, you have already learned beam element, okay, prismatic bar element, okay, but since these are a bar, okay, where you have a force, okay, acting in the so-called transverse directions, okay, so therefore beam element is the best, okay. But then in this element itself, it is a spring, okay, so you can use a spring element over here, okay. So once you have a spring element over here, you just assemble them together, okay. You have a stiffness matrix for this, stiffness matrix for this, okay. This one you use the spring stiffness matrix, combine them together, assemble into the same global stiffness matrix. You can solve them simultaneously, right? So that would be the idea, okay. So meaning to say, you can see that you can combine different type of finite element, okay, into your problem, okay, to solve it, okay, according to the function of it, okay. Therefore the selections of the finite element is very important, okay, to represent the whole functions of the structures that you want to you intend to solve here, right? So far no questions, so we will proceed with the next part of this topic, okay. So as you can see in the beam, okay, not only we should not only consider the concentrated load, okay, we should also consider the so-called distributed load, okay. This is very important, especially when you have a very long beam, okay, and the beam itself have a weight, okay. That weight contributes to the displacement, okay, the bending of the beam member itself, okay. Therefore we would want to solve for the distributed load, right? But then, as we have said it previously, we cannot apply if we intend to take this as an element, okay. This is a beam element. The element itself, the load only can act at the node, okay, but not at the middle of the element itself, okay. So what we need to do is we have to readjust or redistribute, okay, or resubstitute all this, okay, into an equivalent load acting only at the node, okay. That is our main idea to solve for the distributed load for a finite element methods, okay. So what we can do is we have to represent this into this, okay. So again, we can represent it with bending moment as well as reaction force, okay, on both ends itself, okay. So what we can see here is that the weight multiplied by the length give us the total load acting on the whole elements, okay. So because this is a force divided by length, right? So if we multiply by the length, then we know what are the total forces acting on the bar itself, okay. So what we need to do is we assume it is equally distributed among the two nodes. Therefore we use the total load acting divided by 2, okay, because it is being supported by two node itself, right? So same thing, we can recalculate the moment, okay, and it is given by the WL square over 12, right? So you can try to how should I say, get the summations of the moment, okay, across it, okay, due to the distributed load, and you will get this parameter, okay, eventually. Okay, again they are equals, okay, so that they will not bend heavily on one side, they should be equals, right? So these are the two important equations here, okay, to represent a simple distributed load. Okay, based on this idea, now we can easily break them into parts, right? So if this is the case, okay, it is only acting on the segment 2 to 3, okay, segment 2 to 3. Therefore this distributed load we can change it to the WL over 2, okay, WL, because it's only considering the length of this from 2 to 3, right? So WL over 2, okay, then the moment is WL square over 12, okay, so you just add them on the both side, okay, on the both side itself, okay. So eventually you will get this form, right? But if you want to further break it down, okay, you don't want it to be not 1, not 2, not 3, not 4. If you want to have 5 knot, okay, now you take not 1, not 2, not 3, not 4, and not 5. Let's say you want to add an additional knot at the middle, so that your result is more accurate, okay, because later on you will see why we would want to add a knot at the middle, right? Okay, so now if you want to add a knot at the middle, therefore the formulation is similar, okay. You just take these small sections, okay, break them into small sections. Therefore these small sections will have a length of small l, okay, small l. So the weight will be W small l divided by 2, W small l divided by 2, okay. Moment remain the same, okay, W small l square over 12, and so on, okay. Then do another one for the other side, okay. Then since this is acting at the same point, okay, this is summations, okay, and this will cancel out each other because they are acting at the different directions but equal magnitude, okay. So eventually you get this as the whole free body diagram, okay. Now if we would want to see how I would say using the work equivalent methods to replace the distributed load set, okay, what you can do is we just integrate it along the length with the distributed load, okay, multiply by the length, okay, and multiply by the force, okay, the vertical displacement itself, the V, okay. Therefore that would give us the work, okay. And due to the work, now if we break them into parts, okay, break them into many parts, then therefore you have these 4 components, okay, M1 phi 1, M2 phi 2, F1y V1, and F2y V2, right? So it is very similar to all the independent degree of freedoms, okay, of a beam itself, right? So if we consider the uniform load of the beam, now you can see it is given in this way, okay. Therefore the discrete part should be equals to the distributed part, okay. Discrete part means you just take them into only one, okay, taking these 2 part discrete only, okay, like elements, okay, equals to this parameter, okay, the distributed along the bar itself, so there should be equals, okay. Then from there equate them, okay, solve it, and you should get these equations eventually, right? So this we will not go in detail, okay, but the idea is that Once you get there, okay, then later on what you can do is you can take any node, okay, at any length, okay, again like the shape functions, okay, you can take any point equals to 1, the rest equals to 0. They should give you the moment, okay, which is, you can see, is equals to WL square over 12, okay, which is what you put in previously, right? Therefore, on the other end, on the other node itself, okay, this is for node 1. For the node number 2, you get the same answer, okay. So eventually you can see that we have derived the values for the moment, okay. Same thing for the force, okay. You get LW over 2, LW over 2, okay, which is what you have applied, okay, into your equations previously, or your free body diagram previously, okay. This is how you can derive it, okay, to get all these parameters, okay. So again, any questions, if you have, feel free to put into chat box, as well as if you have it later on, you can post it in the WhatsApp group as well, okay. So now again, we will just go through the idea of transforming this distributed load into the finite element form, right? Finite element form, okay. Therefore, very straightforward. This is very straightforward equations, okay. This is W, okay. So for, if we just want to break them into two nodes, okay, node 1, node 2 with one element, therefore at element number 1 it should be WL over 2, okay, WL over 2, okay. For the moment is WL square divided by 12, okay, WL square divided by 12, okay. So very straightforward, right? Then on the solution itself, okay, on the solution itself, okay, once you have break them into this is now similar to what you should do for a beam element, right? So what you need to do is you discretizing the beam itself, okay. Since this is one element, okay, then we just use the one element to solve it, okay. So one element, therefore remember we say this is a symmetry stiffness matrix, okay, for the beam. Therefore we just use this, okay, multiply, okay. Then on the displacement side, this is the displacement. On the load side, okay, so here is the load, okay. So this load itself is what you have seen here, right? So you can see that you have the force at node number 1 minus WL1, okay. At node number 1 we have a moment due to the wall itself, okay. There is a moment, okay. So M1 minus the moment due to the disputed load, okay. Then on the other end there is no support, so therefore no external force acting, therefore only the WL divided by 2, okay, as well as the WL square divided by 12, okay. Then from here substitute it, solve them, okay, substitute all the boundary condition and then solve them simultaneously. Eventually you should get your answer, okay. So you just substitute, okay, just hard work, slowly remove, okay. So eventually you get your answer, right? Okay, so yeah, so you will get the effective global forces and then the corrected, okay. You can see that this is the WL over 2 and so on, right? So now what you need to do is you have this form, okay, which exists over here, okay. So what you need to do is just to bring it over the other side, okay, bring it to the other side, okay, so that you get what you need, okay, at the final solutions, okay. So bring it over to the other side, okay, minus them out, okay, then eventually you will get the actual force, okay, because in the if you only solve for this one, okay, if you only solve for this one, then what you get is this value, okay, but our intention is to know what is the forces and moment acting at node number one, okay, therefore you have to do some mathematical operations, okay, shifting it from one side to the other side, all right, so eventually you get this, okay, whereas for the node number 2 you don't expect any force and moment, right, so you should get 0 over there, okay. So to verify again, you can use any simple relationship, summations of force and summations of moment should be equals to 0 to verify them, okay. So same thing for equations or the examples 4.7. You can not only use the distributed load, but in this case they apply a concentrated load at the middle, okay, but as we say, if we want to apply a load, it must be on a node, okay, so there are two ways to do it, okay, either you add an additional node, okay, at the middle, okay, break them into like this, or in this case they want to show you that you can also break this into the two equivalent so-called load at the two ends, okay. So if you intend to break this into two, therefore the equations would be the total force or the total load, okay, P divided by 2 on both ends, okay, whereas for this would be PL divided by 8, okay. So you can break them into two separate load, okay, to represent one single concentrated load acting on the single bar, right. So this is important because you can see that this L is important to denote, okay, with the locations of this P, okay, it can be over here, it can be over here, right. So that would tells you how you can locate it accordingly, okay. So same thing if you have now non-uniform distributed load, okay, therefore you have this triangle, right, you can form a triangle over here, okay, another square as well as a triangle over here, right. So what you need to do is combine them together part by part, right. So for node number 1, okay, you can see that this is, let's take element number 1, element number 2 over here, okay. So what you can do here is that depending on the triangle, okay, depending on the triangle, but usually since this is a straight line type of triangle, therefore the formulation would be in this way, okay. So you will have this, okay, to represent the element number 1, okay, to represent this triangle, right. So that triangle itself is given by minus 3 WL over 40, okay, and then you have a load, okay, acting, which is, sorry, the load itself is W minus 3 WL over 40, the moment itself is minus WL square divided by 60, okay. So same thing for the other side, this is the load, okay, and this is the moment, okay, due to this non-uniform distributed load, okay, this non-uniform distributed load, okay. So same thing for the other side, okay, you should have something similar, okay, 3 and 7 should be there, 3 and 7 should be there. The only difference is that this is the uniform part, right. So what you need to do is, if you intend to derive it, you can try to add them up, okay. So eventually we get 13 and 17, as well as as well as for the moment itself, it would be 7 divided by 120, and this one will be divided by 15, okay, for this particular side, right? So eventually you should get this particular form, okay? So this is how you can derive it for a non-uniform linear varying distributed load, okay? So next would be the last sections, okay, just to give you an idea, okay, how good is this finite element solutions, okay, as compared to the theoretical, the exact solutions of a beam, okay. You have learned the exact solutions in the strength of material using the beam theory, right? Okay, so let's take these examples, okay, a cantilever beam problem with a distributed load, okay, uniform distributed load, okay. What happened is that if we are using only a single element, okay, you can see the result is dotted line, okay, dotted line, okay, whereas for the beam element is the solid line. All right, so you can see that the exact values that match the beam theory is actually occurs at the node, okay, okay. So therefore, as we say, okay, if you intend to get the exact node, okay, you can add an additional node, okay, so that you break them into two elements, so that this middle part would be correct, right? So the solutions for the displacement will match the beam theory at the node, okay. Then from the displacement, to get the moment, we differentiate it respect to x, okay. Therefore, this curved line now turns into a straight line for the beam, for the finite element, one element, okay. So once we turn this into a straight line, therefore now you can see that this is the solutions for the exact solutions, okay, the solid line. Now the best approximation for the bending moment, okay, would be at the midpoint of the element, okay. So if you want to get the best bending moment, okay, it would be at the midpoint, okay, of the element, okay. If we further differentiate to get the shear force, okay, further differentiate this moment to get the shear force, so this straight line, if we differentiate further, we will get a straight line, right, a constant, okay. Then again, the best approximation point would be at the midpoint of the element, okay. So if you intend to get only the exact displacement of the beam, therefore you can add a node, okay, at the middle, okay. But if you are not intend to do so, okay, you want to know others shear force and other things, then you don't need to, because the best approximation would be at the middle of it, okay, of the element. All right, so if we intend to further improve the finite element solutions, either use more elements, okay, by refining the mesh, okay, instead of one straight line, you can add 1, 2, 3, okay, more elements, right? Then you should get more proper line, okay, or bending, okay. Whereas for on the other node, okay, you may also know that we can have a derivations for an element with a mid node, right? Mid node, okay, meaning to say this is still one element, okay, with a mid node, okay. By having this mid node, or we call it a higher order element, okay, therefore if we have one mid node, therefore you have 2 degree of freedom, 4 and 6, okay. So therefore 6 parameter, and this displacement functions now will be very much in this form, okay, is in the in the order of 5. Okay, therefore in this way you can also improve the result of the finite element. Okay, so far what we use is 2 node, okay, and the 4 the power of 3 polynomial line, okay, to approximate the displacement. Okay, so this is the the model that we use, okay, to derive for this, okay, the displacement function for it. Okay, therefore if we intend to improve, either add more elements or use a higher order element, okay, higher order element which have the mid node, okay, to increase the solutions. Okay, so that's all for today. Okay, since we have covered sufficiently from week 1 until today, week 4, okay, week 5. Okay, so I guess it will be the best time for us to have the first test next Thursday. Okay, next Thursday, okay, 22nd April, 2 p.m. Okay, just take note on this. So the topic cover would be on what, the spring element, okay, until today the beam element. Okay, so you have the spring, prismatic bar, and the beam. Okay, so 3 particular part, okay, to cover for this test, right? So if you want to get good results, what you need to do is get ready. Okay, there are questions for you to practice, okay, selected for you from the book, okay, textbook itself, okay, in the slide. Okay, so you just scroll past through this slide, you can see a few questions for you to practice. Okay, so make sure you try it, okay, to solve it, right? And from there you will get an idea, okay, how all these parameters comes in, okay, and play a role, okay, to get the answer, right? So any more questions before we call these sessions to an end? Give 1 minute to wait. So if no questions, then we will end these sessions and we will meet again on this Thursday. Alright, so see you and stay safe, everyone. Okay, bye bye.